Okay, all right, thanks. We can get going here now. Thanks everyone for coming. It's a pleasure to introduce for our special Colloquium talk today, Dr. Shambhu Ghimire. He's a lead scientist and principal investigator with the Stanford Pulse Institute, which is part of the SLAC National Accelerator Laboratory. And he started off with his PhD in physics from Kansas State University back in 2007 and went on to do a postdoc at the University of Michigan. And then he joined SLAC in 2009, where he's been investigating the broad field of attosecond science and nonlinear optics. Along the way, he's been recognized as the prestigious Young Investigator Award from the U.S. Department of Energy, and he's going to tell us today about high-harmonic spectroscopy of quantum materials. So thanks for coming.
Thanks, Jason, for a nice introduction. Yeah, it was a real pleasure to come here and get back to sort of a normal life after 2 years of being, we all are being trapped. It was a pleasure to get back into the flights, and believe it or not, I even enjoyed the short layover, but that was at Vegas. And the title of my talk is High-harmonic Spectroscopy of Quantum Materials. And in this talk, the research material that I use are from the experimental and theoretical work that is supported continuously for a long time, over decades now, from the U.S. Department of Energy. I thought I would begin with something very simple that everyone knows, and perhaps everyone here actually feel proud of this experiment. That was the first observation of second harmonic generation by Peter Franken in 1961. Of course, this experiment, together with other theoretical works, such as the spectacular work of Bloembergen in perturbation theory and related experimental works that all occurred in the 60s, right, which was the gold rush of nonlinear optics, and really founded this field that we are all proud of today. Here you might notice the exact this little dot of second harmonic spot. This was the copy. That was the submitted copy before the editor had the chance to manipulate famously that he thought that there was a dot or something and removed from the publication. But this experiment actually has a very sort of a turning point in my career, and that's also the reason why I'm showing you this. I was traveling in different universities at the time when I was looking for postdoc positions, interviewing different universities, and happened to visit physics department at University of Michigan, which was this Randall laboratory, this 4-story building. That when I was there, I realized of this experiment, although the experiment was really old, right, and I thought that the building actually had the legacy. And that actually had some impression on me that this was the place, a right place for me at the time. Now, since I gave you the clue that you probably found out about this original dot, right? How I got it, and since I started working in that, I was on the 4th floor, as a postdoc. Not on one of those nice fishes with windows and everything, but on the back side, right, there was no window. But I drew little, snow on the wall, and because it's Michigan, so that's how I enjoyed. And I thought that I should do an experiment that has something to do with high-intensity laser and crystal. And this is what I came up with after a lot of thinking, because there was the laser damage issue was the main issue where people could not apply intense laser pulses to the range that I was interested to. And sure enough, when I used short mid-infrared laser pulses, in a zinc oxide crystal, I was able to observe very high order harmonics, as you see here, like up to 25th harmonic orders. It's kind of like, seeing just like in Peter's experiment, instead of 1, we're seeing like 25 dots, right? And this is so many dots that the editor cannot ignore, but instead they thought this was a really spectacular experiment and represented in the cover of the magazine. So we'll come back to this, the detail of the experiment in a little bit, but it turned out that the underlying microscopic mechanism was actually quite rich, and even that this Bloombergian theory, the perturbation, the theory that is based on the perturbation theory, actually completely broke down when we try to explain these experimental results. And since the observation, there has been a lot of progress in the field, the entire ultrafast laser science community, and even reaching out to other communities such as condensed matter physics and material science communities. So it has been a very exciting decade where many groups explored the underlying microscopic mechanism, and I will tell you all about this today. Okay, but I want to begin with some highlights and tell you that based on those understanding, what is this high harmonic generation process is useful for. Okay, let's start like that. And it turns out that one of the strengths is to be able to probe the electronic band structure of the source material that you use, including the topology of the material that you use, and similarly, because we use the strong laser pulse for excitation, and there is some interesting periodicity in crystals that you can do really interesting mixing of the laser periodicity and the periodicity that is present in crystals, and come up with some very interesting light field induced new novel quantum mechanical states that are not available naturally. And of course, because it's a noble light source, right, that has the high density and periodic target, and this could lead to a compact attosecond light source, and that could be also the natural strength of this process. Okay, so here is my detailed outline of the talk. Here I will start from the atomic picture. It actually turned out that this high harmonic generation process was actually well understood in the atomic case for a long time, like more than 3 decades now. So I will take that. I will take the opportunity to compare what is new in solids with the atomic case, and I will give you a very tutorial description. I expected, and I hope I'm right, to have lots of students in the audience. And finally, at the towards the third or last third of the talk, we'll discuss some interesting new results on 2D crystals and topological insulators. Okay, so you might have, as a student, you might have. When you saw the advertise for today's colloquium, you might have thought that there is some guy coming from some complicated national laboratory, right, and going to talk about some complicated stuff. What you will find out, I hope, is that there's all the experiments that I run in my group are actually tabletop experiments. That are mostly run by 1 or 2 graduate students, undergraduate students, and they're technically really simple experiments. Just like as I said earlier, we have 25 spots, right, that we measure. We look at the polarization, and then we take advantage of the crystal orientation and things like that. And finally, we do come up with really interesting optical physics insights. But technically speaking, the experiments are very simple. Let me begin with this atomic high harmonic generation picture. Here, what happens is that this mechanism was understood in the early 90s. Here, this is a 3-step process. This is known as the recollision model. Here we have a Coulomb potential. This is basically how the electron is bound inside an atom. The outermost electron is bound in an atom, and that's the Coulomb potential, right? But this is dressed by the strong laser field. Therefore, it is completely like bent down like that, okay, depending on the direction of the field, right? And when this barrier is suppressed, this electron can actually tunnel through this already suppressed barrier and can actually leave the atom and go very far, okay. And what happens is that since typically lasers have, these are sinusoidal, the electric field reverses its direction in the next half cycle, and during this acceleration process, what we call the acceleration of the electron actually have to return because the field actually changed its direction. It went from positive to negative, right? So it would come back, and then with some probability, it's gonna hit the same parent ion, right? Same atom, which is ion now that it came out from. So when it does that, the electron has lots of kinetic energy based on these parameters of the laser, but the ion is huge compared to the electron, right? That large kinetic energy has to go somewhere because the ion is not going to move, right? So what happens is that all the kinetic energy essentially comes out in the form of this high energy photon. Okay, so this is what happens inside one cycle. Typically, right? Okay, let me first show you a more compact form of what happens in this one cycle. Right, these are three steps. The electron was tunneling out and coming back and recombining. Typically, in the experiment, you have like many cycles in the laser pulse, like maybe 20, 30 cycles and things like that, right? So then what happens is that, if you produce one emission in one cycle, or maybe let's say, like every half cycle one emission, right, is closer to, closer to half cycle than one. So if you have 20 cycles in the laser field, okay, and you produce one harmonic photon in one half cycle, you have like 40 emissions, right? So what happens then? What you collect is kind of similar to what happens in Young's double slit experiment, right? You might remember in Young's double slit experiment, if you have one slit, you have a pretty broad stuff, right? But when you have two slits, you have a nice interference pattern. Discrete like fringes, right? It's just like that. Here, instead of two slits in the Young's double slit, we have 40 slits. And what you observe in the experiment is something like this. They're basically very discrete. These are the fringes, discrete lines. Okay, and depending on the spectrometer. So we only image in one dimension. So this is a line. If you image in two dimension, there will be a dot, like in Peter's experiment. Okay, so here this nice frequency comb, if you like, are these peaks are separated by twice the laser frequency, and they are in atomic medium. They are like all odd order harmonics, only that you observe because of the symmetry. And the maximum energy that you get, which is called the high energy cutoff, here in this experiment, this came out directly from my thesis. But the original experiment was, of course, done in the 80s. This is the high energy cutoff, the 100 eV. This is the maximum energy that I was able to produce with the parameter that I used at the time. And this scales quadratically with the electric field of the laser. Okay, so that comes out becomes useful later. This can be as high as up to kilovolt if you have a very long wavelength or very strong electric field. Okay. So what is this useful for besides the interesting light source? All right. So I will just give you one example, one or two examples on how this was used. This mechanism was used as a spectroscopic tool, and this becomes useful in understanding the solid state spectroscopy. As we discussed earlier, the electron went out, right, and came back. Okay, and then this recombination was a coherent recombination, right? And if the target was a molecule, molecules typically have interesting geometrical structure, right? If it had some interesting geometrical structure, as shown here, a very simple diatomic nitrogen molecule, right? Then, depending on which direction the electron actually came back to, it's going to see the molecule differently, right? So it's sort of like, you're taking the selfie. You're sending the electron out, and then the molecule is taking its own selfie. Okay, and in the experiment, what you measure is the angle dependent. You align the molecule and measure the angle dependent high harmonic emission. Basically, the efficiency of the generation as a function of different angles, and you compare this to some isotropic medium like atom, and you come out with this beautiful, picture of the orbital that is, that might remind you, even if you took, the modern optics, modern physics or early quantum mechanics. These are the HOMO orbitals, right? And on this process of when it is coming back, right? If anything happened to the target itself, if there was some interesting dynamics that is going on in the target itself, because for example, in some bigger molecules, there could be some interesting dynamics. You also can probe what happened in that molecule, because you can so precisely control the time at which the electron would come back and recollide. Okay, because you have the knob of the laser wavelength, for example, as shown here. And when they did this, they were able to actually experimentally probe on this molecule how the whole density was moving from one side of the molecule, like here, to the other side, and then coming back in a really fast time scale, in fast, femtosecond time scale. So this tells us that using this high harmonic spectroscopy as a tool, you can probe both the structure and dynamics of the target. Okay, of course, this was a very semi-classical picture. There is also a fully quantum mechanical model that supports much of what I have just told you. Now we go back to the solid. Okay, so one interesting thing that we actually measured during the first experiment was this high energy cutoff scaling was actually linear to the electric field of the laser pulse. As we said, right, in the gas phase it is quadratic, so it was linear. So these scalings are pretty strong, tools to tell you about to give you some ideas of the underlying microscopic mechanism. So immediately we thought that there is something new about these solids, right? That's not present in atomic systems. So let me just to make this more clear, let me put these pictures side by side. This is the atomic picture that we just saw, right? And this is the solid state picture in a very simple form. As I do this, you can immediately see, okay, in solid, right, which is a periodic array of heavily packed atoms basically, there is something very similar to the atomic case like recombination, okay? But there is also something very different, which is shown here in the green. So this is called the block oscillations. If you are a student from the ultra cold atom groups, you probably know what it is already. But I'm going to tell you. So here we have a periodic potential, all right, and instead of the atom, we have a charged particle electron that is moving in the periodic potential. In the periodic potential, when you have a particle being forced with certain electric field like E, so it's going to actually wiggle. So that's what the block oscillation is. Okay, so this wiggle frequency is linearly proportional to the electric field, and it's also proportional to the lattice. Okay, so in a very simple picture, you can see that by measuring the cutoff energy of the harmonics, you could learn about the periodic potential about the material, right? And also this could potentially describe this noble mechanism that is present only in solid materials. In the solid state, at times, its real space picture is more difficult to understand. So you go to the momentum space picture or reciprocal space picture because of that reason. So for a comparison, let's first convert this atomic model to a reciprocal into a reciprocal space picture. Okay, so actually very simple, right? So the energy is basically the square of the momentum, right? Everyone knows. And here those three steps are intact. what you are looking at here is the flat parent ion, the ground state if you like, and this electron is basically very far from the atom, and it's basically freely running, running in the electric field of the laser, right? So that's the free electron motion, and this can be viewed as this parabolic band or continuum if you like. And at a certain point in time, right, you tunnel here. At a certain point in time, this electron recombines with the parent ion, and this difference energy comes out in the form of a harmonic photon. Okay, is that clear? Okay, now let's move on. Well, now what happens in solids, right? So solids is first of all, there is a band structure picture, but I will tell you how the band structure even arises. Okay, so you have one single atom. You had that type of energy, right? When you have you bring in another atom, and there is some overlap to the other atoms in the proximity, and that overlap is essentially represented by these arms, like sort of like developing wings. These represent essentially the overlap to the other atoms. Okay, so there is something called the nearly free electron model for the band structure, and you basically deviate from that and find out you come to some real band. This is a cartoon just to make illustrate the idea. And when you do that, so there is one thing, the block oscillation. So that channel, right? We just talked about the block oscillation in the real space. That's the emission. So here in this language, it is the emission from this single band motion of the electron. Here, it was also a single band motion, but it was parabolic. So just if the electron was just running in this parabolic band, it would not radiate. It had to recombine. But here, because of this higher spatial components, you have the higher order Fourier components, if you like, in the current, right? And those are the high harmonics. So that's the first channel. The second channel, which is very similar to the recombination in atomic case, right? And this is the channel 2. So maybe channel 2 wasn't very obvious, so I'll run you through very slowly with more details here. So here, this is again a 3 steps model in the solid state. Usually, in semiconductors, you have a valence band that is completely filled, and you have a conduction band that is completely empty. Okay, so we start with that. With the laser pulse, you excite some electrons to the conduction band, leaving behind holes on the valence band. And the same strong electric field is going to drive those electron and holes in their respective bands. And at some point in time, this electron could now recombine to this hole, right? And this is already step 3. And this difference energy of the electron and hole basically gives you the amount of the high harmonic photon, the energy of the high harmonic photon. Okay, now you could ask, right, why I have to recombine right there? Why I could not recombine even before? You could, right? There is not, you could recombine anywhere, because it's a basically driven polarization. So if you recombine at lower energy, this vertical axis is energy. If you recombine at this energy, you have a lower harmonic energy photon, okay, and even lower and so on up to the band gap. So now you could say, oh, if I had a way to measure those emission times of the harmonic photons, I have a way to measure the band gap, right? So this is exactly what this group at Ottawa proposed and to some extent realized in the same zinc oxide crystal by measuring this emission times of harmonics and reconstructing, at least to some level, the band structure of the source material. There is a similar really nice work from Lepterich's group when they were at MPQ, where they took the channel 1, right, the block oscillation channel, and they probed the crystal quartz, the conduction band of the quartz. So those are the reciprocal space applications. Harmonics can probe, at least they have the strength of probing the electronic band structure. Of course, there's a lot of details there, right? But I just wanted to get the meshes, like, very illustrative meshes using this very semi-classical picture. Now, in the real space, we spend some time in the real space. We use the magnesium oxide crystal. And this is also a very simple experiment. All you do is you take a crystal and you rotate the crystal and see how the efficiency of harmonics changes. And this is the raw data. Okay, kind of similar to the nitrogen molecule experiment, right? So here you can see the strong emissions along certain directions, and almost essentially nothing in some other directions for a linearly polarized laser field. And the nice thing of the laser is, you can play with the polarization of the laser itself, right? So we did. So our student did. So he changed the laser from linear to elliptical and to fully circular, and basically watched how harmonic intensity changes as a function of polarization. And that's the raw data. Okay. And then he got out from the lab and he had to think about what the heck is going on in there because of this maxima and minima and so on, right? So we spent a little bit of time to do a very semi-classical, very simple calculations. We only consider the band structure of this magnesium oxide crystal, and basically, we analyze, we trace how the electron would move in the crystal. Okay, if you are driving with the electric field, with certain electric field, certain polarization, how they would be basically moving in the crystal. And this is what happens in the linearly polarized laser field. This is it gets more interesting in the circularly polarized laser field. But without going into details, the idea here is that if this electron trajectory is going to find the nearest neighbor of another atom, it's going to radiate more. Okay, so if it's going to find the second nearest neighbor, it's going to produce the secondary maxima. Okay, and believe it or not, in solids mostly things are empty. Okay, and if it doesn't find anything in the proximity, right, then it produces nothing. Close to nothing. So that's the basic idea. So you use now you have a way to use material's own electron to do essentially coherent electron diffraction in the material. Okay, so you might think, okay, so what are the other prospects? Like, I talked about the compact light sources, right? How is it different from the existing, gas phase high harmonic sources? So here is one example. Also, really nice work from the same group, from Threedimensional group. So what they did here is, without even going through the complicated, experimental measurement. So I will just tell you the results. They measure how the photon energy of harmonics change as a function of laser intensity. Okay, it's a pretty slick experiment. Why? Because lasers typically fluctuate, right? When the laser fluctuates, the photon energy of the harmonic could also move, right? You want to know, what type of dependence you have. So the top is the gas phase. There is certainly a significant change of the photon energy as a function of laser intensity. This is the solid quartz, which is much more sturdy, as you can see. Similarly, there is also dependence on what's called the carrier envelope phase, which becomes important for really crazy short pulse like a single cycle or 2 cycle pulses. And they observe the same thing. In the gas phase, there is lots of deviation, and in the solid, things are much more stable. So we did a similar experiment on magnesium oxide crystal. This is what we did. Also, this is much simpler experiment than the previous MPQ experiment. Here we instead of doing harmonic generation in only one spot, we have 2 spots. Okay, we split the beam into 2 beamlets and then focus to the sample at 2 different places, just far enough that the lasers do not talk to each other, the fundamental, but close enough that you have a way to this the harmonics that we produce in the far field, they actually overlap both space and in time. Okay. And when you overlap both in space and time, this is what you see. It's a spectacular, fringes on all harmonics. This is in the XUV. It's really nice. I shared that because the fringe width is basically the wavelength of the laser, right? So this is XUV. This is crazy short wavelength, and therefore it's a crazy fast time resolution. And this is in the attosecond range. So that's the setup. So the experiment is following. The experiment is, now we change the relative intensity between these two spots. Okay. So, and then basically watch how these fringes evolve. That's it. So these are the results. First, we did this experiment in the transmission mode. Two spots, harmonics are coming out from the other side of the crystal. The crystal is 200 micrometer thick. And this is, we are tracing the harmonic photon energy as a function of the relative intensity between two spots. Okay? And this is in the reflection mode. You clearly see the difference, right? So in the transmission mode, things are going in one direction, moving up, or in the reflection, they're moving down, right? So that's just one example of how strong this XUV spectroscopy can be, right? The reason why this move down by so much is because of this propagation effect that is occurring in the crystal. So there is a paper that talks about this in much more detail. What I will tell you today on this is just that we use the same platform to study how this fluctuation depends on the different materials. Okay, the fluctuation meaning that the shift of the harmonic photon energy as a function of relative laser intensity, how that depends on certain source materials. Okay, so here we compared magnesium oxide and quartz. And we find that in magnesium oxide, the fluctuation is much bigger than in quartz. Actually, consistent to the MPQ experiment, they use quartz, and we also find much smaller deviations in quartz compared to the magnesium oxide. So, welcome to the wonderland of solid state. You have lots of varieties of solid materials, and you have a new way to control this dispersion, the phase of the harmonic, XUV harmonics that you can produce. That's just one example of the strength that the solid state gives you that you did not have in the atomic and molecular case in the gas phase. Okay, so the rest of my talk is on quantum materials, but this completes my tutorial talk, and wanted to make clear by showing you the semi-classical picture. As I said earlier, there is also a fully quantum mechanical version that is available, and that is consistent to for major observations, both model actually work. Okay, so now before I move into this quantum material stuff, I would like to give the opportunity to students. If you have any questions, is the time to hear from you regarding the tutorials. Yeah. Are you a student?
Yeah.
Okay. You're qualified.
I was just wondering if this might be captured by the complete quantum picture of what's going on, but it seems using the semi-classical picture, you can generate photons of higher energies at any sort of continuous frequency, right? Not necessarily just at the harmonics, right? So how do you reconcile that?
Yeah. So if you had a pulse that had only half cycle, right? There you actually do that in terahertz range. You can actually have a half cycle pulse. If you had a half cycle pulse, meaning that pulse had only positive side, right? You would expect to have an entire continuum, no discrete harmonics. So these discrete harmonics basically come from having multiple half cycles, many cycles. So this can be reproduced easily either from the semi-classical as well as also from the quantum mechanical model. Yeah. Any other students? Come on, Moshe. Make it short, okay? Make it short. Go ahead.
Because materials do not have a band structure, presumably, but they show some properties of having band structure, like semiconductor amorphous materials. Would you get high harmonics if you did the same experiment on amorphous materials, or would it be a continuum?
Yeah, so actually whether it is harmonics or continuum, it doesn't have anything to do with the the amorphous, whether it is, there is a caveat, but generally it has nothing to do with, whether it is amorphous or a crystal, but rather just on the number of cycles in the laser, right? But the caveat out was that in amorphous materials, you have inversion symmetry, right? And so we compared crystal quartz with pure silica. So both are beautiful. Quartz produces both even and odd order harmonics because there is no inversion symmetry, right? And that was the reason why also Franken saw the second harmonic. And in fused silica, you see both odd and even harmonics because there is a the crystallinity is gone, right? So and the efficiency wise, they are very different. So there is a Nature Communication paper. If we get time, we can talk about that in more detail. So actually, it was we using the idea of this different wavelength, because this excursion of the electron can be different for different wavelengths, right? So we changed the wavelength and went from 800 nanometer light to up to around like 1600 or 1800 nanometer, which changes the excursion significantly, right? And comparing, doing this experiment on fused silica, we were actually able to measure the grain size of the material. Yeah, so it's actually a very interesting, phase transition probe that you might like that in the memory materials when you go from crystal to amorphous and vice versa, that this will probe. Okay, let's leave it at that. And so let me move on. So the one of the quantum materials is two-dimensional crystals that you might know. So why the two-dimensional crystals are interesting? Okay, let's give me one shot at that. This is the picture for this is a 3 dimension, this is 2 dimension, and this is a picture of an exciton. Okay, if you do not know what exciton is, I will tell you. Exciton is basically electron and hole. They are bound together. Okay, pretty much like how the electron is bound, right? If you have a hydrogen atom bound to the nucleus of the hydrogen atom. That's it. Okay, in a very simple picture. Of course, there are different types of excitons and all that, but I think for this discussion, that is enough. Now, if this is my electron, this is my hole, and I can draw some field lines, very much like how you guys drew your field lines in your magnet experiment. Like you had a bar magnet, right? And you had a compass, and then you followed the line, right? Those lines here, and you can see that in 3-dimensional system. These field lines need to go through the material. But in 2-dimensional case, it's a single sheet of like 1 or 2 atoms thick layer, monolayer. Those field lines do not need to go through the dielectric material, and therefore, this reduces the screening. Now the electron and hole can be strongly correlated, like and this gives you the opportunity for external control. So you can put in other methods, other environments in the atmospheres to be able to do some interesting perturbation to the systems. So this is just one example of why the 2D stuff is really interesting. So we took the example of MOS2 because it's a prototypical 2-dimensional crystal. And this is the bulk, right? I'm looking at here from the top of the crystal. Okay, same thing here, but this is a single layer. So you should be able to see the difference between the single layer and the bulk. So the single layer does not have reflection symmetry or inversion symmetry on this plane. Okay, the bulk is basically average of different layers. They are oriented, they are mesh-oriented, if you like, by 60 degrees. But when you have so many layers, in average, there is a reflection symmetry. Okay, but that description is actually enough to explain the qualitative features on this spectrum. This is the harmonic spectrum, a portion of the spectrum that we observed from 3-dimensional MOS2. Okay, this is the spectrum from single layer MOS2, and sure enough, you see the additional even order harmonics that we just talked about, right? In the case of this broken inversion symmetric system. So this was interesting observation, but actually there was something more to it that draw our attention quickly, which was this. we looked at the polarization of these even order harmonics. Okay, so usually the harmonics have the same polarization direction as the laser field. This is how in the gas phase things are understood, and because there is no dipole to radiate in the transverse direction. Okay, so here what we found out is that actually these even orders are orthogonally polarized completely to the laser field. Okay, so there is something unexpected at the time. It took some time for us to understand. So I will give you a very simple analogy here for the interest of time, but I will want to get my message across. So there is a very interesting, very popular condensed matter physics phenomenon called Hall effect that you might know. So what happens here is that you have a metal and you apply some electric field and magnetic field along these two directions, and what you observe is something called the induced Hall voltage. It's in the perpendicular direction to both the applied electric and magnetic field. Okay, so in the same analogy, we have a crystal, we have a conduction band, let's say, we have this electron in that band. Okay, so this is tilted just for the illustration. And usually there is the standard term, which is just the group velocity of the electron, and also there would be another term, and this omega is what's called the Berry curvature, and this is kind of like the artificial magnetic field. So if you remember the Lorentz equation, so sort of like this, so it acts like, because of this interesting symmetry properties of the crystal, the electron here acquires the transverse motion in the band. Okay, so we argue that now, since it was driven in the transverse direction, right, the polarization is also in transverse direction, and it's actually with that theory. In the quote-unquote theory, in a semi-classical description, you actually have an interesting approach. If you put a cube polarizer here, since the harmonics are in the visible range, you just have a way to do a polarization spectroscopy, and you have a way to probe the moving electron in a band, and the probe the dynamics in the orthogonal direction. That's the all-optical approach that is analogous to the Hall effect, right? So what's the big deal? The big deal is following. Because it is all-optical approach, this allows you to measure the dynamics that are occurring in the natural time scale of electrons and hole. So that is the big deal. Okay, so now, and of course there is a fully quantum mechanical version of this theory that is available in this first in this paper, and maybe more in the more recent paper that just came out last month. Yeah. Here.
The one before, sorry. Why did the even order harmonics increase in intensity? Normally the odd orders always decrease. Why do you go from 6 to 8 to 10 to 12 increasing in intensity?
Yeah, that's actually a very good question. So we don't have a very good explanation for it. The explanation is that the working explanation is that, as we shared before, there are two mechanisms. One is the intra-band, like single band mechanism. Another is the two-band mechanism. And it turns out that for high order harmonics, which are above the band gap, the one mechanism dominates over the other. And the other side of the band is the reverse. So that comes into play, and when to explain this, you have to use this now fully quantum mechanical model, because these dynamics get coupled, right? So there is no easy explanation, but but there is a fully quantum mechanical model that considers the it's not the simple inter and intra band picture, right? Things are coupled, so that does reproduce this increase, and I suggest you find our recent paper. That's what we talk about. The paper is in ultrafast science. That's the new journal. Yeah. So good question. Okay. So another type of quantum materials that you might have heard, which is three-dimensional topological insulators. So I will tell you what it is. Okay. So you don't have to have any physics background on this lecture. Now, but this is the raw data. This is the band structure of bismuth selenide, which is a prototypical three-dimensional topological insulator. I will explain to you what are the main features. There is a band gap. Okay, the bulk of the crystal has a band gap. This is the valence band. This is the conduction band, and this is exactly around is almost exactly 0.3 eV. Okay, so bulk is an insulator because it has a band gap. Right, doesn't need to be insulator. It could be metal, but but has depending on the Fermi energy, but it has a band gap. Okay, now you see these are the surface bands, and surface bands, they actually close. There is no band gap. Okay, kind of like the surface of the material was fully conductive, like a metal. Okay, and on top of that, these bands are protected by what's called the time reversal symmetry protection. So you have to flip the spin to go from this side to this side. Okay, so that's my 1 minute introduction of three-dimensional topological insulators. So in our spectroscopic approach, we wanted to find out what is the signature of this topology, right, into our high harmonic spectrum. How do we separate the contribution from the surface, contributions between the surface and bulk? Because optical laser goes through both the surface and bulk, right? So we want to be able to separate this, and then eventually, if we find those signatures, then what we will have is a way to probe a phase transition in materials, topological phase transitions, when materials go from one topological phase to, let's say, non-trivial topological phase to some trivial topological phase. So the trick here is just that we have to come up with a laser that has the photon energy much smaller than this band gap, the bulk band gap. So that was the only trick. Okay, then this is the experiment. Again, very simple experiment. We rotate the crystal, okay, linearly polarized light, and sure enough, we see all harmonics are polarized in the same direction. And the crystal structure is also such that if you are looking from the top, the first layer has some planes that do not have inversion symmetry. Okay, and like as shown there. So this is dotted line is the mirror plane. When the laser is polarized in the direction of the mirror plane, everything is polarized in the same direction. Okay, when the laser field is polarized not along the mirror plane but somewhere else, like at 30 degrees, we produce these even orders. They flip the polarization and they become orthogonal. Okay, and this is very similar to MOS2, and yet it may not have anything to do with the topology. It's just the inversion symmetry broken system, which is the surface, right? Now we're interested to find out really what is the signature of the topology. Okay, so I'll tell you a brief version of that. So this is again the calculated band structure. We start from the tight binding model. This is the bulk band. This is the surface band. So we have this nice single Dirac cone here. These are the transition dipole moments between these two bands, and the same thing here between those bands. And you notice something here, especially here. There is a vortex feature at the center, and that is a reminiscence of spin momentum locking. Okay, I'll tell you what it is. You don't have to worry about that. So there is always a simple explanation. So this is it. So this is the momentum, x-axis and y-axis. Those arrows represent the spin. Okay, so all I'm saying is that the spin is always in the plane here, on the plane of this board. That's the surface of the material, right? And the spin is always in the plane, as well as always perpendicular to the momentum. Okay, so as soon as you see this picture now, you kind of think that, okay, there are some things with some handedness, right? So it's a left-handed system, right? So, and the expectation is that if you come in with the left circularly polarized laser pulse, then you're going to kick this thing hard. Okay, so that's the expectation. And of course, there is a fully quantum mechanical model is there on this PRA. This is all theory. The experimental results are just accepted in nanoletters last week, but there is a archive version that you can look at. So these are the results. First on theory, so we are plotting harmonic intensity, just one selected harmonic. The behavior is very similar on all harmonics. Is that the intensity of harmonic drops significantly in the case of the bulk when you increase the ellipticity. Okay, when you go from linearly polarized laser to circular polarization, linear polarization was you expected a high intensity, but for the circular polarization nothing for the bulk, right? Because bulk does not have this spin momentum locking. Okay, so you have to make this. I have to make that clear, which I forgot earlier. The surface, on the other hand, has the highest efficiency for the circular polarization. Okay, now so let me show you the experimental results. These are the experimental results of using a really thin film bismuth selenide, and the intensity of harmonic basically plotted as a function of ellipticity. Okay, pretty simple experiment again, and sure enough, you can see qualitatively there are some details. Qualitatively, this looks very similar to the emission that we expected from the topological surface states. Okay, so there's lots of details here that you can read if you're interested. This was really excellent work that was done. The experiment part was done by Denitsa, and the theory from Alexis. So now we have a signature, right? The signature of the topology is the dependence of the harmonic efficiency for circular polarization. Okay, so now we are going to do some interesting chemistry here. So we change the topology of the material. It's actually our collaborators did from Rutger. They introduced some impurity in the material. Okay, so this was the experimental, close to pristine sample where there was a Dirac cone to start with. They added some impurities, and then basically they were at high impurities. This Dirac cone disappeared completely. Okay, the topology, the non-trivial topology is gone. So we take those same sample and do our high harmonic experiment. And here, this was the data. This is the data from the pristine sample. Where the signal is maximum for the circular polarization, and this is the data for the 20% impurities. First thing is the efficiency is generally very weak, 4 times weaker. The second thing is that the enhancement for circular field is completely gone. Okay, so this is still a work in progress, but I think this opens up lots of opportunities to probe phase transitions in materials, and including the light field induced phase transitions. That would be really interesting to probe with this all optical approach. Okay, so I'm going to just finish up by telling you a couple of new potentially future experiments and theories that we could do together. Together with theorists here. So there is this is Moray lattice is one of the hot topics now in condensed matter physics, right? But it's also a really interesting optical crystal, I would say, and it could lead to a very interesting optical experiment. We are interested to. I mean, maybe I should give another 1 minute on what the Moray lattice is. So you have a graphene sheet, 2 graphene sheets. Okay, they are slightly misaligned, and when you do that, you give rise to a completely new periodicity that you see here. Okay, in this big plot, and not only that, the band structure. There is something really interesting. What's called this the density of states. They get picked up, and this even the material even becomes a superconducting, and all that exciting stuff that is going on in the community. And you might know the work from Leroy group here at the physics department that this can be realized in TMDCs. So I like TMDCs more because they have certain band gap and they have a high damage threshold for the laser. So the experiment like as they shown the Moray pattern on this material, it would be really nice to probe the Moray lattice with high harmonic spectroscopy.
Professor, what do you mean by TMDC?
transition metal dichalcozanide. Basically, those are the type of this, like the sulfur. This selenide, right? The sulfur. Those are the TMDCs. Just the name. Okay, so yeah. So before we can actually handle Moray, which is so far, at least to me, it's a tough thing to align and also get all the parameters right. So what we started doing is we started to basically understand layer by layer. So by misaligning or aligning these layers of these two-dimensional crystals ourselves. So here, this is the natural orientation. That's how it comes up. Like this molybdenum and sulfur. Those atoms are arranged like this. And in what we can do is we basically take the if you have a so the other day my daughter was asking me what is the 2D crystal, right? So this is my 3D book or whatever this is, and I take a piece a paper out from here, right? So then this is a two-dimensional object. So essentially it is that. So you take one layer of the crystal out, and that's a two-dimensional thing. Now, so the way these papers are arranged, so I don't want to break my book. So the way the papers are arranged is like this, naturally, let's say, right? You take them out, and then you reorient them and put them on top of each other, okay? So that's the picture, AAA. So that's what it means. So
How are you physically in the lab actually doing that delamination?
yeah, that was the second question from my daughter. So she's 7th grader. I had a hard time to explain. But what I told her was that I take the Scotch tape and then just stick it and then put it there. Of course, this is not exactly what happens. So they use, but the idea is the same. So they use gold tape. They exfoliate on the gold tape, and there is some cleaning procedure. You need to get rid of the gold and all that. But it's really interesting process. So you have a way now to arrange these layers however you like it. Okay. So in this arrangement, these are the actual people who did these nice things. And when we do this in the same arrangement, like when you line up these atoms, which is called this AAA configuration, what we find out is that the harmonic intensity actually increases, okay, as a function of number of layers quadratically as expected. Okay, so optics makes sense, right? So I think this is just our first step to be able to get handle on a various number of layers, and eventually we want to reach to the Moray physics. Make it turn in this interesting material science problem into also interesting optical science problem, if you like. And just finally, there are some interesting theoretical predictions that we could test, which are on creating and controlling novel quantum mechanical states in interesting materials. You basically take advantage of the strength of the light field that you can manipulate, and harmonics could probe that. And finally, this is my roadmap, if you like. So you're here, right, 2021. So also the summary of my talk, what I told you today is that this is a very interesting high harmonic spectroscopy, the interesting spectroscopic approach. It's not completely new. It's been tested really well in the atomic and molecular systems for some time, and we are trying to understand, or at least in much of the simple materials, we sort of understood, the whole community put the effort and understood this mechanism. Although there is some surprises in quantum materials, but this is where we are. And eventually, we would like to be able to create, control, and probe these predicted novel quantum mechanical states. These are my colleagues, which I'm really proud of. At Stanford, my group collaborates with the groups of Professor David Rees, with the group of Professor Tony Hines, and more recently with the group of Professor Fang Lu. For theory work on topological insulators, we collaborate with Alexei Chacon at Postec, Korea. Samples were grown, some batch from University of Michigan, and more recently from Rutger group, and the original zinc oxide experiment was performed at the Ohio State. And finally, just want to leave you with some biographs of how my lab would look like, and these are all tabletop experiments that that a couple of students put together. And sometime you get a famous individual that you might recognize. You are supposed to recognize, I should say, in our visiting and inspiring us in our labs. Thank you very much for your attention.
Where you were talking about the effect of elasticity, your theoretical graph has a peak at the zero value for elasticity, whereas in the experimental it's a null, which is what you'd expect from how you described it.
Yeah.
Is there a good explanation for that anomaly in the theoretical calculation? For the
there is a hopefully leading good experiment that we could do here. That Jason and I just talked about this in the morning. So he has a nice. First of all, let me speculate what this feature is. So we think that this feature, this dip, is a destructive interference between the emission from the surface and emission from the bulk. That cancels out here because the bulk emission at the linear is relatively strong, right? And it would be really interesting to do. What Jason has is the dual frequency comb that we produce harmonics from the surface in one of his comb, right, and then from the bulk from the second comb, and have them interfere and really dig into this and find the origin. And then not only just finding the origin, but you could lead to a very interesting, all-optical way to probe electron interferometry between surface and bulk bands. It would be really interesting, to extend this to topological materials generally. Thank you.
Just an effect on those, the single layer stacking kind of thing. Do the sheets kind of are they able to be stacked at kind of any angle, or are they specific angles that work well and specific angles where the molecules will kind of bond together correctly?
Right. So remember, the one of the reasons why the stacking is done in this so-called layered material is that these layers are there is a very weak coupling between multiple layers. Okay, so they are called van der Waal layer, right? So if you like, a good explanation is, this Getco, like like in the Geico advertise, right? These things climb on the wall, right? How do they grab onto things? So that type of force is very weak van der Waal force. So that means there is no strong coupling between layers. They are just barely touching, but barely interacting to each other. So in that sense, this theoretically you could have any angle, but now it comes down to how good you can align those things, and we're exactly we're working on that exactly. And in graphene, it's crazy. You need to have like crazy good resolution down to 1 degree. That I think I had in the slide. We are not working on graphene yet. The nice thing of the TMDCs generally is that they have for some reason the bigger angle that you can work with, like 3 degrees. That gives the Moray pattern, right, in the data that I showed, the data from the physics department here. So so a little bit easier maybe in the TMDCs, but it is really down to the experimental uncertainty. It is how you can it's just basically aligning two crystals on top of each other.
When you explain the coupling between the spin and the linear momentum, you said there's a certain directionality to the coupling. So if electricity goes to left circular polarization, you get more absorption. But here your electricity goes from -1 to +1, so you have both right and left, and you have a strong intensity on both. So that means you have both right and left helicity for the spin.
Yeah, so let's see if I had the new data. Okay, so maybe, yes. Yeah, we actually spent some time on that, and so maybe, I don't know if you can read them. So this is sort of what we saw earlier, the same data but taken at a different time, different day, and, but it's the harmonic fifth. So it was a line out. This is the whole thing, right? You're looking at this x-axis is the ellipticity, linear in the middle, left circular and right circular. Sorry, the other way around. And this is the crystal orientation on the vertical axis. Okay, and so if you are looking at exactly at the left circular or right circular, it is extremely difficult to say if there is a chiral, like because we have to be extremely careful to actually be able to say if the response is chiral or not. But what we can do is it's much easier to look at somewhere in the middle. Okay, so this is still ellipticity. Let's look at the seventh harmonic, right? So here you can see, so here this is left elliptically polarized light. Okay, so here this is right elliptically polarized light. Okay, so they are not mirror image. So that means they are chiral. The left hand is different from right hand. So in this finite ellipticity range, it is really easy to describe. The fully circular is a little bit tricky, but yeah. So maybe I will leave it that, and maybe we can discuss more later. I guess maybe tomorrow. This could lead to really interesting the chiral strong field physics, especially on the oil semi-metals, where the material is actually the whole 3D is chiral. So there you clearly see the chiral response. Here only the surface is chiral, not the bulk, right? And also there is an unavoidable coupling between the surface and bulk. So that makes the fully circular is a little bit complicated to say anything, to declare anything. But in the medium ellipticities, they are very there is a pretty clear chiral response you see everywhere.
I had two questions. The first is that can you provide a comparison of your electric laser field strengths with the field strengths that electrons naturally experience in a crystal?
Yeah.
The reason I ask is because when you probe something with light, you have to wonder, like, in atoms and molecules also, one has to wonder, when the harmonics are produced, does the light probe the natural structure of the material, or is it somewhat like modified structure of the material?
Yeah, very good question, of course. So first of all, let me define what the strength, how the strength of materials compared to the laser field we drive with, right? So let me even give you one example. Zinc oxide crystal has the 3.2 eV band gap. Okay, so the lattice spacing, the distance between zinc and oxygen is about 3 angstrom. Okay, so that means the binding strength, roughly speaking, in that crystal is 3 eV per 3 angstrom. Okay, so approximately 1 volt per angstrom, right? So that's the strength of the material, the interatomic binding strength. The laser I used in the first experiment was 0.6 eV, 0.6 volt per angstrom. So that means that's the comparison. And if you have a shorter pulse, you can drive even with the higher field. So this is really like the strength, the interatomic binding strength in the material is actually comparable to the strength of the electric field, the strength of the pulse. So that's the first part of the question, right? The second part is whether or not you're probing, what you think you are probing, right? So far this semi-classical description I gave you was assuming that the things are frozen. So band structure is frozen, and then we just excite a single electron or a single hole, right, single particle essentially, in the frozen system. So that's the assumption. Now, of course, this assumption could break down in a lot of cases. Certainly, for example, in strongly correlated electron systems, right, where the band gap itself could go crazy. Right. For example, nickel oxide is one of the strongly correlated electron systems, especially as a function of the strong electric field. Right. You could completely close the gap, right, in presence of such a strong field. So those things would be really interesting to see how experimentally and more importantly how theorists would predict that kind of the harmonic response from the dynamic system, if I would like to call like the dynamic system, right. So far. What mostly the community has done, is on the frozen system so far. In the what we call, as you know, is the single electron, single active electron approximation. Basically, everything is fixed. We drive a single electron or single electron hole pair.
Can I ask another question? Yeah. So my second question is that it's a very versatile technique, seems like, but there seems to be a lot of potential in also probing the dynamics. For example, one could, with one pulse, impulsively excite the phonon modes, or coherently excite the phonon modes, and do phonon spectroscopy by using a second high harmonic generating pulse.
Yeah.
So have you thought about it?
Yeah, absolutely. Yeah, so we can do experiment tomorrow, okay, just like that. But the problem is, what is the theory? Right, so there is no theory that can describe the generation from such a dynamic system. So so you can I expect to see some interesting wiggles as a function of the driven phonon motion, right? So I think what we lack is the experiment. So yeah, that's a challenge for if we have theorists in the audience. But it would be really interesting. Actually, could be extremely interesting to use his stuff. Right, meaning that the two combs where you can actually delay these essentially two combs, two teeth, with respect to each other, even to really long time, to like nanosecond or longer than the phonon lifetimes, right, and still have the good temporal resolution. Yeah, so this is one of those things is maybe we can draw interest from theory groups doing this calculations where they can predict the dynamic response. So we're not there on the solid state systems yet, but experiments I can promise you that they are pretty feasible. You just need to get it down because we do the phonon spectroscopy directly from the reflection, right? And we have the tools. We know what is the signal to noise resolution, signal to noise ratio, and those things that we need. But there's just not a theory that is available to that would help to understand what we see.
You mentioned that there was some theoretical work being done on TMDCs. I'm just wondering at what level, for example, the full quantum system you solved the Dirac block equations for the full non-equilibrium system. Are you talking about that level of theory, or is it something different?
Yeah. So of course I'm an experimentalist, so I'm not representing theory groups here. Although we wrote a fully theory paper, that was our pandemic thing because lab got shut down, and and my postdoc and I basically turned ourselves into theorists for a short time. So I think the correct answer could be that we use semiconductor block equations, and we can also start from some standard tight binding model. So tight binding model more or less reproduces main features of the band structure, right? And then even of the TMDCs, and then we use that. So that's the limit. So what that means is that of course, the first thing, the tight binding doesn't really reproduce the entire band structure. It only does well, close to the zone center, close to where the band gap is small, right? So there are some ideas like a group at Hamburg, for example, does the TDFT calculations. I showed their theory predictions. So that is all theory. So there they can do the real TDFT calculations, but that's not something I have expertise. In our level semiconductor block equations are sort of right now the state of the art. And which is still, it's kind of nice. I like it because this is where you can change parameters, right? You have the model, you can change the parameters of the band structure, and you can turn off certain bands as you like, which you cannot do easily in TDFT. So that's really the advantage that I like. So it's that is certainly a challenge for the theory groups to be able to include, and especially the correlations. Which correlations in semiconductor block equations, the only knob we have is the dephasing time that we insert phenomenologically. Yeah, and there is an interesting, hopefully interesting archive paper that is available where we basically change the dephasing time and then understand how the harmonic intensity reduces as a function of the initial population.
I'll be talking to you tomorrow.
Okay, thank you.
My colleague, can you join me tomorrow? This guy does the full Okay. What is TDF?
Time-dependent density function theory. So DFT is a density function theory, right? TDFT, you add a T.
Great. All right. Well, thank you very much. Dr. Ghimire will be here through tomorrow, so if there's time to follow up on conversations, we can track him down. But let's thank him one last time. Thank you.